Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed this phase diagrams for 1D model, and then we have discussed about 2D model for like a coupled system and uncoupled system. So, in that sense, we have just to find that for this like one dimensional system, we have visualized that whenever we are just going for phase diagrams, we are just finding first the steady states, and once the steady state is achieved, then at that point whether this system is unstable or stable, so that we can just take from these phase diagrams. And whenever we are just analyzing, we are just finding that if suppose we will have like a positive slope there, then the point at which it is just occurring, that represents an unstable condition there, but if it represents a negative slope there, then it just provides also a stable condition. And in a 2D uncoupled system, it is easy to get the solutions, and especially we have just tried to find like the steady state points, and at that point we have just determined this Jacobian to find this like eigen values, and depending on the eigen values we have predicted that whether it has a like stability or instability is preserved. But if we are just going for like coupled system, then especially we have reduced again to a uncoupled system or to a matrix where this diagonal entries are there, and depending on these eigenvectors plotting, we have just find it out that whether this point is stable or unstable. And in this lecture we will just go for a like a qualitative approximation of this differential equations, that is phase diagram 2 here. So, how we can just say that this whether we are just approximating this functions with like a linearized system, and whether this linearized system which is represented as a Jacobian matrix form is providing a exact solution whatever we are just expecting from this analytical overview of these equations. So, that we will just analyze with this lecture. So, first we will just go for like a phase diagram of a 2D coupled nonlinear system, since as I have told in the last lecture we have discussed for 2D coupled linear system, and this nonlinear system can be dealt with that two methods, that is first one is Hartmann-Grobman theorem and second one is like a Lyapunov function, and this can be analyzed through Knoll-Kleins also. So, then in the final phase of this lecture we will just go for this Knoll-Klein of chemostat model. So, any nonlinear system, it can be represented as we have discussed in the last lecture, that the generalized representation of system can be written as like y dash equals to f of y, where y is a vector of size n. This means that we will have like a system of n equations here, and if it is a nonlinear system of a differential equation, first what we are doing is we are just linearizing that system, and if f of y is linearized about steady state points, then especially we are just using this Taylor series expansion for this. In the last few lectures we have discussed that Taylor series method, how we can just analyze these things. This means that we are just assuming these two functions, that is in the form of f of x plus h y plus k and capital G of x plus h and y plus k, and we are just assuming this functional values which is represented as x dash equals to f of x y and y dash equals to g of x y, that assumed to be 0. Then we will have like first derivative terms present in the Taylor series expansion, and from there itself we are just getting this Jacobian matrix. This is nothing but the linearization technique we are just using to get this nonlinear differential equation to a linear form here. And once we are just obtaining this linearized system, so then we are just using this phase diagram to analyze whether we will have like a stable condition where it is just preserved there, if we will have like steady state points. So, for this analysis, if you will just consider a 2D system like y1 dash equals to or y1 prime is equals to minus y1 plus yn q, and y2 prime is as minus 2 y2 here. So, first if you will just find the steady state of the system, we will just keep this y1 dash equals to 0 and y2 dash equals to 0 here. If you will just put these two values 0 here, then from the first equation we can just get it as like y1, if you will just take common here, then y1 square minus 1, this equals to 0, and second one we can just get it as y2 equals to 0 here. And from the first system we can just get either y1 equals to 0 or y1 equals to plus 1 or y1 equals to minus 1. Hence, the steady state of the system are like first point it is minus 1 0 and second one is 0 0 and third one is 1 0 here. And if you will just go for this Jacobian of this system, so Jacobian especially we can just write it as like matrix of first differentiation with respect to y1 here. So, that will just provide you minus 1 plus 3 y1 square, and second no y2 is present there. So, that is why this will take 0 value, and third one if you will just differentiate with respect to y1 here, this there is no factor associated with y1 here. So, that will just give 0, and last value if you will just differentiate with respect to y2 here, that will just give you minus 2 here. Hence, the diagonal entries for Jacobian matrix, it is just written as a diagonal as minus 1 plus 3 y square minus 2 here. And at different points, like since we have just defined p as minus 1 0 here and q as 0 0 here and r as 1 0 here. So, then at these points like p and r, since this is a square function, it is present here. So, that is why this minus 1 and plus 1 both it will just provide the same value. So, that is why at point p and r, if you will just see the value of a Jacobian, it is just represented as a diagonal of 2 minus 2 here. So, this means that along the x axis it has a like positive value, along the y coordinate it will have a negative value here. And if you will just go for this nature of a phase diagram here, we will have a saddle behavior around respective steady states here. Since if you will just see here p as the points like minus 1 0 here, then q as the point as 0 0 here, and r is the point that takes as 1 0 here. And if you will just analyze this behavior of this phase diagram here, at the point q you will have this like value as minus 1 q, it is 0 0 here. So, if you will just put 0 0 value for this Jacobian here, we will have these values as Jacobian equals to like minus 1 minus 2 here. So, both these values are negative here. This means that diagonal entries are negative, means you will have this eigenvalues are negative here. So, the nature of the phase diagram will be converges towards the point q here, since both these eigenvalues are negative here. And if you will just see this like the overall nature of this phase diagram, that is at the point q, if you will just see at the point p, suppose if I will just see here. So, if I will just put minus 1 0 here, so minus 1 means if I will just put y1 equals to minus 1 here, so that will just give you 3, then 3 minus 1, this will be 2 and minus 2 we can just get. So, 2 minus 2 means you will have a positive value 2 and a negative value minus 2 here. And along the x axis if you just see, so that eigenvalue is 2, that is why this will just deviate from that point. And if you will just see along the y axis here, the eigenvalue is minus 2. So, that is why these points it will just move closer towards 0 0 here. This means that this is minus 1 0 here, since whenever we will have a minus 2 means it will just push towards that point, and whenever we will have a like positive value, it will just retarded from that point. So, this phenomena is occurring at both these points p and r, if you will just see, that is minus 1 0 and 1 0. Overally, if you will just see p and r, this will just give a unstable nature here, and q will be the point which will just provide a stable nature for these equations. And if you will just go for like further analysis of phase diagram of a nonlinear system. So, in the previous example we have studied the qualitative nature of the system after linearizing the same about the steady states. And as you know that always whenever we are just linearizing the system, it is just a approximation to the system, not the exact system we are just considering for the solution process. So, whenever we are just approximating the system, whether this has represent the same qualitative behavior as shown by the original system or not, that we have to check also. So, that we can just check. So, this means that whether this original system and linearized system will behave exactly the same or not. And if you just go for this analysis, so we can just consider these equations like 18.1 and 18.2, if you just see here. So, y dash equals to f of y here and y dash equals to j y. So, this is the approximated or the linearized system we have just considered, and this is the exact system we have just considered here. And so, whether this system, both these sides on the right hand side, they are just behaving like steady states at the same level or not, that we will just discuss here. And this query was resolved by two famous mathematicians, one is Hartmann and another one is Grobman. So, if we will just go for this theorem that is developed by Hartmann, Grobman. So, the statement of the theorem states that suppose we will have a nonlinear system y dash equals to f of y, and its linearized form y dash is represented as like j y here, since we are just using this Taylor series expansion to linearize the system. Obviously, many methods are available, but we have just picked one method, that is a Taylor series method here around the steady states. Then both these equations will show the same qualitative behavior only if steady state is hyperbolic. Then the question arises that what does mean by hyperbolic here. So, the statement for hyperbolic is that a steady state is termed as a hyperbolic if the associated Jacobian matrix has all its eigenvalues with non-zero real part. So, at best we will have like a real part which has certain values except 0 to provide that the system is in, or the state is in hyperbolic phase. So, in the previous example, if you will just see, all the eigenvalues were having non-zero real parts. This means that if you will just see that we have just discussed here, that is the diagonal elements are coming as 2 minus 2 minus 1 minus 2 here. So, that is why all real parts are existing. Hence, we can just say that the system is hyperbolic in nature. And that is why the statement states here that the three steady states already we have discussed in the previous slide, that has like a non-zero real parts, hence J was hyperbolic in all conditions. And hence we can just say that the behavior of a linearized system will be same as that of original system around steady state by the condition of a hyperbolic system. Since the theorem states that if you will have a system like y dash equals to f of y and its linearized form is expressed as y dash equals to j y, that we have made it, and around the steady states, then if you will have a existence of a real part, then we can just say that this qualitative approach of this approximated solution is exactly equals to the real system solutions. So, the question arises that if the steady state is not hyperbolic, then what we can say. So, for that a method due to Lyapunov is very useful in determining the stability of nonlinear system about non-hyperbolic steady states. So, if we will just go for this Lyapunov function, then we have to comment on the stability of a nonlinear system around a non-hyperbolic steady state y 0 here. So, first we need to assume a Lyapunov function. How we can just construct this Lyapunov function, that we have to concentrate. So, for the Lyapunov function, first we will just determine a function as suppose v of y satisfying v of y 0 equals to 0 and v of y greater than 0 for all y not equals to 0. Then if we are just assuming these conditions, so based on this differentiation we can just assume that whether the system is stable or unstable or asymptotically stable. So, if we are just assuming this function v of y as the Lyapunov function here, so first condition we are just assuming v of y 0 equals to 0, v of y greater than 0 for all y is not equals to y 0. Then if v dash y is less or equal to 0, conditionally we are just assuming both this v dash y equals to 0 and it is less than 0 for all y in the domain, then y 0 is stable. And if v dash y is strictly less than 0 for all y is not equals to 0 in the domain, then y 0 is asymptotically stable. And if v dash y is greater than 0 for all y not equals to y 0 inside the domain, then y 0 is a completely unstable point, or the system will be unstable at that point y 0. And if the condition remained is that v dash y equals to 0 only, then the trajectory of the system lie on the surface by v of y equals to constant, since this will just roam around that point level only. So, for this we have assumed a function, that is example we have considered here. So, suppose the system is represented as, suppose y 1 dash equals to minus y 2 q here, and y 2 dash equals to y 1 q here. And for these systems, if you will just see, the steady points or the steady state points are like first one y 1 dash equals to 0, then you will have y 2 equals to 0, and if you just consider y 2 dash equals to 0, this means that y 1 equals to 0 here. So, the steady state point is 0 0 here. And if you just consider this Jacobian here, then the Jacobian will be represented as a first differentiation with respect to y 1 here. So, there is no term associated with y 1. So, that is why it just take the value as 0 here. And if you just take differentiation with respect to y 2 here, that is a minus 3 y 2 square. Second function, if you just differentiate with respect to y 1, this is a 3 y 1 square here. Second, there is no presence of y 2 term. So, that is why this will take 0 there. And if you just see this Jacobian, clearly we can just find that these eigenvalues are 0 and 0, since the diagonal entries at the steady state p here. So, the steady state p 0 0 is since we do not have any like real part, like a non-zero real part. So, that is why this 0 0 is the non-hyperbolic, since by the basic definition of a hyperbolic we will have like a non-zero real part. So, if it is like non-hyperbolic, then we can just use this Lyapunov function. So, if we will just formulate this function v of y in such a fashion that v of 0 0 equals to 0 and v of y greater than 0 for all values of y except 0 0, then the simple function satisfying these properties can be written as v of y equals to y 1 to the power 4 plus y 2 to the power 4. This is a guessed corrected method, since exactly we know that we do not know how this behavior of this function will perform there. So, now if you will just take this differentiation here, since the next condition is that we have to find that v dash y, it should have either less than equals to 0 or greater than 0 or less than 0 or equals to 0, that we have to testify. So, if you just see here v dash y, that is nothing but the differentiation if you just take for this function here, we will have like 4 y 1 q, y 1 dash plus 4 y 2 q and y 2 dash here. Already y 1 dash it is known as minus y 2 q and y 2 dash is y 1 q. If you just put all these values, we are just getting this value as 0, since both these quantities are equal here. So, the trajectory of the phase diagram, it is just given by v of y, which is written as y 1 to the power 4 plus y 2 to the power 4, this equals to constant here, that we have just defined in the previous slide here. If v dash y equals to 0, then this will be defined as v of y equals to constant here. And if it is constant, definitely you have known that this nature is periodic and it will move inside a circle, since it can be written as y 1 square plus y 2 square, this equals to constant. So, it will just move inside the circle, hence the system is stable here. So, not asymptotically stable. And whenever we are just discussing about this Lyapunov function, so we should have to take care it in seriously, since this is a guessed correct method, and by assumption we are just considering this function. If for any assumed function you are not able to decide for sign of a derivative of the same, you should try with another possibilities. So, suppose if you will just consider a function like vy as y 1 square plus y 2 square, then v dash y, it can be written as if you will just find the derivative here. So, 2 y 1 into y 1 dash plus 2 y 2 into y 2 dash here, and y 1 dash is defined as minus y 2 q and y 2 dash is y 1 q. If you just put all these values, then you can just find minus 2 y 1 y 2 into y 1 square plus y 2 square. And in this case you cannot say that whether v dash y, it will just give you this like positive or it is negative or it is equals to 0, that is doubtful. You cannot comment on the stability of these conditions. So, you should have to be careful whenever you are just defining this Lyapunov function. So, then we will just go for null clines, a systematic way to draw phase diagrams. So, till so far we have learnt about phase diagram and then analyze the stability of the system. Whenever we are just drawing these phase diagrams of linear and nonlinear system, we used the concept of eigenvalues and eigenvectors. Already we have discussed that whenever we will have like a uncoupled system, we have used the eigenvalues. Whenever we have used coupled system, then we have used these eigenvectors. And for nonlinear systems, we have used like our Lyapunov function for non-hyperbolic functions, and for hyperbolic function we have used also the same eigenvalues there. And here we will just study an easy way to draw the phase diagrams for nonlinear functions. So, if you would have observed here, the steady state of a linear system is always occurring at the origins, and similarly the nonlinear system, it can be calculated by solving this first order differences equals to 0 also. And instead of solving these equations algebraically, if we can just solve them with the help of graphs, then this is called null clines. And if you just suppose draw this graph of like yi dash equals to 0, then it is called yi null cline, where I is any index. So, the basic idea is that directly we are just putting the graph of yi dash equals to 0 here, and from the different graphs intersection points we can just find the steady state points, and after that we can just visualize that whether the system it is just performing at different point levels, how it is just performing. So, if we have to do this like stability analysis using this null clines here, we have to put some points, that is when null clines are used for 2-dimensional systems, it can be used, and they are exclusively used for nonlinear systems, since null clines cannot be used everywhere. So, there is some certain restrictions. So, that is why we have just put this statement as note that null clines are used only for 2-dimensional system, and they are extensively used for nonlinear systems, that is for 2-dimensional nonlinear systems. And if you will just go for one example on null clines here. So, suppose consider one nonlinear system given by x dash equals to y square minus x and y dash equals to x minus y here. So, first to draw this null clines, we have to put x dash equals to 0 and y dash equals to 0. So, if you just put x dash equals to 0 and y dash equals to 0, we will have this equation that is in the form of y square minus x equals to 0 or y square equals to x, which represents a open parabola or a parabola opening rightward having vertex at 0 0, that we have just represented here. And the second null cline, if you just see here, that is y dash equals to 0, that is nothing but x minus y equals to 0, which just provides also y equals to x. This is the line, that is the line passing through 0 0 having slope 1 at origin. And whenever we will have this intersection of these two null clines, that will just provide us the steady state condition. If you just see here, these intersection points are occurring at 0 0 and 1 1 here, and at these points if you just see, this just provides us x dash equals to 0 and y dash equals to 0. So, that is why they are the steady state points. And if you just go for this like analysis of the behavior of null clines at different test points. So, we will just take a small perturbation close to the steady state points, and then we can just visualize that how this like perturbed points behaving in the closer neighborhood of the steady states. Depending on that, we can just say that whether it has a like a stable point or a unstable point. So, if you just choose the point like minus 1 1 here, so then we can just find that x dash is taking the value as y square minus x. So, that is why it is just providing the 2 here. So, any point if you just choose here, suppose minus 1 1 minus 1 here, then it is just providing a like a positive value here. So, this means that the points x will increase, it will point forward. So, that is why we have just putting these symbols here. This means that it is just giving a monotonically increasing function. So, always it will try to increase along the like positive x axis. So, that is why it is just the arrows are putting towards this rightward direction. And if you will just consider this function for y dash here, then we can just find that this is minus 1 minus of minus 1, this is equals to 0 here. So, y dash will not change here, because the point minus 1 lie on the y null line here, since this is just lying on this line here, hence y null line is 0 here. So, arrow no arrow, that is why we have not kept any arrow pointing in the vertical direction. Similarly, if you just check all other points, like suppose 1 1 we have kept it over here, then we can just put like 2 1. So, if you just put 2 1 here, so then you will have like a positive value. So, that is why it will just point outwards there. So, similarly at all other points we can just test, and we have just point these arrows in different directions. If it is a negative, then it will approach towards this steady state points, and if it is like a positive, then it will just point outwards from the steady state points. That we can just say from this graph. And if we will just go for this analysis of a null line function for chemostat model here. So, this chemostat model, especially it is represented in the dn by dt equals to alpha 1 c by 1 plus cn minus n here, and dc by dt, which is represented as minus c by 1 plus cn minus c plus alpha 2. Already we have defined this chemostat model in the earlier lectures. And if we will just go for this null line function here, or the null line values, we can just put dn by dt equals to 0 and dc by dt equals to 0 here. And if you will just put this n dash equals to 0 and c dash equals to 0, you can just find that alpha 1 into c by 1 plus c n minus n equals to 0, which will provide one value as n equals to 0 here, and another value, that is c equals to 1 by alpha 1 minus 1. So, both are straight lines. And if you just see this c null line, so then we can just find that this cannot be separated it out here. So, that is why if you will just find n value from this equation, then it can be written in the form of c plus 1 by c into alpha 2 minus c, that is nothing but n is a function of c here. And if you will just plot the graph of c null line, which is a function of c, to analyze the nature of expression as c approaches to 0 here. So, if c approaches to 0, this means that c is a very small value here, then c plus 1, it is also like 1 plus some values are there. So, then n will be very large, and so we can just say that when c is very small, n is a very large for this case here. And if you just plot this points, and if you just go for this null line c here. So, at NC as 0 0, whenever we will have like resources is 0 and the population is 0. So, obviously this point will lies at n null line. So, both will be 0. So, at that point we can just see that whenever n equals to 0 and c equals to 0, the resource is alpha 2 there. So, directly we can just say that c dash equals to alpha 2 greater than 0. So, it will point upward from this 0 0 point. And as we know that the direction of arrow only changes when two null lines intersect. Since we will have this null lines, that is in the form of like n, c, if you will just see here, the null lines are n, c, then we will have another one, that is n c equals to alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1 and 1 by alpha 1 minus 1 here. These are the steady state points especially, I can just say. And whenever we will just go for like c null line function, choose a point having very small c, then we can just find that c dash equals to 0 and n dash will approach to minus n here. So, which is less than 0, hence it will just point leftwards if you just see. And from this graph we can just find that whenever we are just starting with a like initial population level, certain population it is just present here, then resources is plentifully available, then after certain time we can just find that this resources will be like optimized with this population growth level, and finally we can just find that this resources will goes down when this population will get on increase, and in a physical scenario we can just find that whenever this population level it is just in a optimum level it will just reach, then these resources will be reduced again, and then this will decline this population level, again it will just increase. This will just follow a like a cyclic process. And if you just go for this like a physical observation of this null-Klein for this chemostat model. So, when there are no bacteria, we are on the C axis only, and then we are converging towards the value alpha 2. So, this means that if there is no consumption of food, then we can just find that we are left with only initial amount of resources. And as the bacteria start growing themselves, they start consuming the food and grow. When they have like the large population size, they compete for the food, only few are able to survive. Then again this makes the food to be plenty amount, which makes the bacteria again to grow, and the same process repeat and converts to the steady state, that is alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1 and 1 by alpha 1 minus 1. Hence, the behavior is oscillatory around the steady state, as we have shown here, that is the spiral state, it is just showing over in this range here. And finally, we have obtained that the steady state is achieved at like alpha 1 alpha 2 minus alpha 1 by alpha 1 minus 1 and 1 by alpha 1 minus 1. So, in this lecture we have discussed like phase diagrams of 2D nonlinear system, then Hartmann and Grobman theorem, then Lyapunov function, and null-Kleins. So, null-Kleins means it is analysis of like different stable points whenever we will have a 2D nonlinear system. And then finally, we have discussed about this null-Kleins for chemostat model. Thank you for listening this lecture.